recently won the Annie Jump Cannon Award. She also has a really amazing cat called Selkie. It's actually very friendly and will let you pet it even though it's very shy. So, once Jacob misses. Alright, so Bekki will be telling you about TRAPPIST-1, your new tiny red bubble.
Thank you. I'm really excited to talk to you today about a planetary system around another star that Tom introduced in his talk called TRAPPIST-1 and why it might be your new tiny little red home. But before I talk about that distant planetary system 40 light years away, I wanted to start a little closer to home in our solar system and our own planets and moons and talk a little bit about those. So I want to start by asking you, would any of you consider Mars your favorite planet?
Sure.
Yeah, okay. And how about least favorite planet?
Mercury.
No, you would consider Mars your least favorite planet. Okay, yeah, in my professional experience, that tends to happen when someone is dragged along to see The Martian by their favorite sci-fi buff. So, whether you're a Mars lover or a Mars hater, you might have read recently that Mars is going to appear in the sky as big as the moon when it gets really close to the Earth. Maybe you saw it on Facebook. Well, I'm sad to tell you that that's fake news. It's true that Mars and Earth are both going around the sun, and that when Mars and Earth are on the same side of the sun, Mars will look bigger. When they're on the opposite side of the sun, Mars will look smaller. But it never looks as big as the moon, sadly. It always looks extremely puny compared to the moon. This is to scale, whether it's at its smallest size or at its biggest size. So if you want to see a planet that looks giant in the sky, you're going to have to travel. So, for example, you could go to Europa. Europa is a moon that's orbiting Jupiter, and if you look up in the sky, Jupiter looks huge. In fact, instead of making small talk about the weather, you might want to talk about the storm on Jupiter that you can see raging in that giant red spot. But this may not be a very fair comparison because the Earth is going around the sun and Europa is a moon that's going around Jupiter. So if we wanted to do an analogy of seeing a giant Mars in our sky, for Europa it would be seeing Io or Ganymede or another Jupiter moon looking really big in your sky. And it turns out that the moons are so close together that they do look fairly large. Like if you were in Europa, this is what Io and Ganymede would look like. They're not as big as Jupiter, but they're still big enough that you could make out the pizza-like surface of Io and see its cheese, pepperoni, and volcanoes. And if you watched it change from day to day, you'd see a big difference between Io at its smallest size when it's on the opposite side of Jupiter, and Io at its largest size when you're together on the same size. So another difference is that with Mars, you might have seen on this graphic that it had its most recent close approach to the Earth on May 30th, 2016. And like a lot of astronomical events, the next one is not a nice even number. It's not once a year. The next one's July 31st, 2018. So it makes it hard to celebrate Mars Day. But it would be a little different if you were on Europa, because the moons Ganymede, Europa, and Io have a very special orbital configuration. Ganymede takes twice as long to go around Jupiter as Europa, and Europa takes twice as long to go around Jupiter as Io. And this special configuration is called an orbital resonance. So now let's watch Europa, which is the middle one, and see where it gets closest to Io. So here they are. Here's their first close approach. Now Europa is going to go around exactly one time and have another close approach, and go around exactly one time and have another close approach. So if you were on Europa, every Europa year, which would be 3.6 Earth days, you'd have your close approach with Io, and Io would look really big in the sky. With Ganymede, it would be every 2 cycles of Europa that you'd be closest to Ganymede and see a giant Ganymede in your sky. So this is what an orbital resonance does. It lets you celebrate Io Day, which is a very special occasion that occurs on Europa exactly every year. And as you know, you could never have a holiday that doesn't occur on exactly the same day each year. Happy first night of Passover. So there's a big problem with going to Io if you want to experience this awesome orbital resonance, and that's that it's really cold on Io. These moons are so far away from the sun that the surface temperature is minus 200 degrees, so you'd quickly freeze if you tried to go there and see the wonderful orbital resonance in that system. And unfortunately, this used to be your only option if you wanted to see an orbital resonance, but things have changed a lot in the past couple decades. For a long time, people have wondered when they've looked at all the stars in the sky, do any of those stars have their own planetary system? And if so, what are the planets like in that system? And it's so exciting that in the past couple decades, we've changed from this being sort of a philosophical question to it being a real scientific question with the discovery of thousands of exoplanets. Here's just a subset of those exoplanets with some dramatic music in the background. These are some systems that were discovered by the Kepler spacecraft, and as someone who studies orbits in her research, this is just a gold mine for me of really interesting systems. So there's all kinds of orbits in these systems, and excitingly, some of them have orbital resonances, just like Io, Ganymede, and Europa. So for all these systems, if you watch a pair of adjacent planets, they'll periodically pass and line up with each other in exactly the same spot, and sometimes 3 or more planets can repeat their configuration. So this is really cool because you can celebrate Kepler 80c Day, or you can celebrate HR 8799d Day, where the planet every year appears large in the sky on the same day. So these systems are really cool, or I should really say that they're hot, because these systems are either located extremely close to their host star, so they're being heated up a lot, or this system is a really young system, so it's also really hot. So the problem here is not that you'd freeze, but that you'd boil if you tried to travel to these planets and experience the orbital resonance. So even with these new systems, until recently, we were really out of luck if you wanted to have the nice beach vacation that Thomas described and see an orbital resonance. But that all changed with the TRAPPIST-1 system that Thomas introduced in his talk. This is a system of B, C, D, E, F, G, H. Planets are always named after letters of the alphabet because we're not very creative that way. And this is a really interesting system. As we heard about, the planets are packed really close to each other, and they're extremely close to the star. So if you imagine our own solar system, you'd have to go in past Mercury and zoom in 25 times to see how close these planets are to their star. In fact, this system, in terms of scale, looks more like Jupiter and its moons than like a planetary system like our solar system. So you might think, if planets are so ridiculously close to their star, they must be really hot, and they also would be a bad vacation spot. But there's a key difference between our own sun and the TRAPPIST-1 sun, which is that the TRAPPIST-1 sun is a small red star that generates very little heat. So you can have a planet extremely close to that star, and it still doesn't get heated up to a high temperature. It can be a place where you can take your vacation after all. In fact, if we rescale our diagrams so that planets are spaced in terms of how much energy they receive from their sun, then this system starts to look quite a lot like our own solar system. There are several planets that would have a temperature very similar to Earth, at least given certain assumptions about their atmospheres. So a lot of astrobiologists and people who work on planetary atmospheres are super excited about this system. But I'm excited about it as someone who works on orbits because it has an orbital resonance. It has a bunch of them. Each of these planets is in an orbital resonance with multiple neighbors so that you can see them having their close encounters and that the close encounters will repeat in the same configuration. And this tells us a lot about how the system might have formed and is an interesting way for planets to transfer energy. And it's just really cool if you like to see your nearby planet appear in the sky on the same day every year. Here's an artist's impression of the planets appearing in the sky, and they would look extremely large because the planets are packed so close together. So it'd just be like when you're sitting on Europa looking at Io with all its volcanoes. We don't really know what's on the surface, but if you were on a nearby planet, you'd have a pretty good view because these planets are so close to each other. So another way to think about the scale of the system, if we think about the distance between the Sun and the Earth versus the distance between the TRAPPIST-1 sun and its Earth-like planets, it's the same as the difference between a tiny house and a castle. So a castle is a great place to live, but a tiny house could also be a great place to live, depending on your personal home aesthetics. So same thing, the TRAPPIST-1 system, it's tiny, but it still could be a nice place to call home. And maybe it would be sort of comfortingly small where you could keep track of your neighbors really well. So one really cool thing about the orbital resonances in the system, so this is showing the planets. This is an artist's impression, of course. These are their orbital periods. So like if you were on planet D, your year would last only 4 Earth days. And then on the bottom is the ratio between the orbital periods of each planet and its neighbor. And they're all integer ratios. This is the type of orbital resonance that we've been talking about. The cool thing was that when this system was first found, they did not know what planet H's orbital period was because they'd only seen it pass in front of its star once. They didn't see it make a full orbit. But by assuming that it's in orbital resonance, just like the other planets, and this actually tells you a special relationship between the angles of the planets as well, they were able to predict when this planet would go in front of its star and go out and observe it at that time, and their prediction was confirmed. They found that, just as they expected, it had a year of 18.8 Earth days. So that was really exciting for the people involved, sort of like back in the early days when when Leverrier predicted the existence of outer planets in our solar system based on its disturbance of the inner ones. So the big question about this system with these planets so ridiculously close to their star is how did they get there? That's a question that I'm going to leave you with. This is a topic that I'm really interested in my own research because we've now found so many exoplanets that are parked right next to their star. And what we want to figure out is these rocky Earth-like planets, did they form like the Earth? So we think the Earth grew up from smaller asteroids and other bodies hitting each other and gradually colliding together and growing into what we see as the Earth today. Or did they form where the Earth formed? So instead of forming so ridiculously close to their star, did they form further away out of a disk and gas and dust and have that gas disk push them into their current orbits? So this is a really big question for a lot of exoplanet systems, but the distinction with TRAPPIST-1, I think, is that there could be aliens on those planets wondering the same thing. Thank you very much.
That ratio between those months, is it going to help you to observe aliens on the planet, or is it going to be helpful for your research for observing them?
Yeah, that's a great question. So the question was, how does the fact that those planets have those near integer period ratios help with observing them? So now we know where they are, so it doesn't help us in that sense, but it also causes a really cool effect that I didn't talk about. So the method that Thomas described for finding planets, where you see the planet pass in front of its star, only tells you the size of the planet because you see how much light it blocks. Usually we don't know what the mass of the planet is, so we have no idea if it's something like the Earth or it's something made of gas like Jupiter or Saturn. But when planets are near that integer-period ratio, they can exchange energy with each other and they can disturb each other's orbits. And this can actually tell us the masses of the planets too, and then we know what they're made of. So without knowing that, I don't think this system would have been such a big deal because people wouldn't have known what those planets are like. Are they even rocky planets that you could stand on like the Earth? But because of their gravitational disturbances on each other, we knew that they're rocky planets, and that makes it even more likely that they could have life and be something like the Earth.
Any other questions?
Because they're so close together, would they have moons, or would they be like acting as moons when they get close enough?
Oh, that's a good question. Yeah, she is wondering, since they're so close together, could they have moons? And this is such a great question that I think there was just a paper about it published a couple days ago. The real obstacle to having moons is that when you're so close to your star, the gravity from the star tends to dominate over your own gravity. So there's a very limited part where you could actually have a stable moon. So we don't expect a lot of these planets close to their stars to have moons. And I think that was the conclusion of the paper as well. But there are people who are trying to find moons around other planets, maybe by seeing a little secondary dip from that planet. But so far, no one has been able to find any.
Another question? Joanna?
So, is the star very active? Like, I know M dwarfs tend to have a lot of activity, like flares and stuff. Do we know if the planets would really be able to sustain life, or might the star be too active?
Yeah, that's a great question. So, Joanna was asking, these small red stars, they're not only different from the sun in terms of their temperature, but they also have these flares. So they have these very high energy particles coming off the surface of the sun, and that could make it a bad place for life. Like if you have tons of X-rays and UV light going onto your surface, that could actually prevent life from living happily there. That wouldn't be good if we had that here. So that's something that people are considering. It's a good question. I don't know if this is like a particularly active star of this type or less active, but that has been one concern people had about finding planets around these small stars. Small stars like this are by far the most common type of star in the galaxy, so you might think it's the best place to look for life, but it is important to consider whether to actually be a good environment given how much some of these stars are flaring.
One more question.
Yeah, I got a question. As far as being as close to the center star as it is, like the gravitational pull, what would gravity be like on those planets versus what we are used to right now?
Yeah, that's a good question. So the question was, since these planets are so close to their star, how would the gravity be different from on our own planet? So when you would be on the planet itself, the planet's gravity would still dominate, so you wouldn't necessarily notice a difference. But if you're trying to send something out into space, then you more quickly get to the zone where the sun's gravity dominates. So it could be different that way. But if you're just sitting on the planet, you wouldn't necessarily notice a difference.
Okay, one last one.
Why is there no planet A?
Why is there no planet A? Yes, that's a good question. So Elizabeth asked, why is there no planet A? Like, why does it start with B? Which you'll notice when you read about exoplanet discoveries. It's because the star is considered to be object A. And then the planets sadly have to keep up after that. And a lot of times it's in order of discovery. So you might have planet B next to planet G, next to planet I. There's been some suggestions for better naming schemes, but none of them have been adopted because it's hard to get astronomers to agree on things like that.
All right, thank you, Bekki.
All right, so So thank you everyone for showing up. Again, this is our first Astronomy on Tap. I think you've made it a very great success. We will be doing this monthly, so we have another event for May 15th, where we're going to be talking about the life and death of the universe, so how the universe was formed up to today, and then where it's going to go from there, where it's going to die, is it going to not die, continue going on. We'll be long gone by then, so you don't have to worry about it. So please do come back Monday, May 15th at Happy Valley Brewery from 5 to 7 p.m. If you enjoyed today, I think you're going to enjoy it next month. Again, we have our donation boxes up on this chair, and I think that's it. Thank you, everybody, for coming.